This is part 2 of our discussion of crystals. With 4 main types of crystals, we looked initially at 2 types that we talked about even last semester: ionically bonded crystals and molecular crystals. This is the term that we're going to use for those compounds that are covalently bonded. You have a sheet which compares ionically bonded compounds with covalently bonded compounds, and you have examples of those compounds, so make sure that you take the time to go back and thoroughly review that information. Now, today, what we're going to pick up on is the 4 types of crystals and their properties. We've seen this before. We know that there are ionic crystals like lithium fluoride and calcium carbonate, metal to nonmetal, held together by strong electrostatic forces of attraction. And because of that, when you're looking at the properties tend to be that these compounds are going to have high melting points, and they're going to be very poor conductors of heat and electricity. They tend to be hard and brittle. Now, the crystal lattice is going to be forming, and what you'll find at the lattice points at the 8 corners or in the faces or the body-centered position is going to be ions. If you take a good look in your textbook, you'll see that most often you see those chloride ions at the lattice points, and then the sodium ions, which are smaller, will be in the center of each face. Sodium chloride is a face-centered cubic structure. Now, if we look at our molecular crystals, going back, our molecular crystals are going to be things like water and carbon dioxide, held together by these weaker van der Waals forces of attraction. So in contrast to the ionic crystals, these are going to have lower melting points, and they're going to be softer. They're going to be poor conductors. We'll talk about conducting of these compounds in greater detail later. I introduced the concept of a metallic crystal, and here they're held together by metallic bonds, which involves delocalized electrons. If you look at this picture, we have a copper wire, and the kernel, the inner electrons and the nuclei make up the kernel, and then these valence electrons are held loosely by the metal. So, if these loosely held electrons are shown here, what kernel does this electron belong to? It's delocalized. Rather than belonging to one particular nucleus, these electrons belong to the crystal as a whole. And they are considered to be like a sea of electrons. This implies movement. So what happens if you set up an electric current, if you plug it into the wall? As the electrons are pushed in to the wire, the electrons here are going to be repelled, like charges repel. And this causes the electrons to just flow over the kernel, over the kernels that are in the wire, flowing through the wire, creating an electric current. Now, whenever you're talking about other properties, when we go to the periodic table, the other properties of metallic compounds vary greatly. They vary from high to low, from weak to strong, from soft to hard. And so, if you wanted to talk about soft and hard, we know that this first family, the alkali metals, tend to be relatively soft. We have cut into alkali metals in our labs, and we've seen that they have sort of a bubble gum texture to them. They are not hard as we think of most metals. What would be one of the hardest metals? Maybe something like titanium. Titanium is one of the hardest metals known. What about melting points, boiling points? Well, we have gallium over here below aluminum, and gallium has such a low melting point that when I take gallium and hold it in my hands, it will soften and start to melt. What about tungsten, though? Tungsten's completely the opposite. Now, I've drawn a very crude light bulb here, incandescent bulb, and you know that there is a wire that runs through it. And what happens is the electricity is run through the wire, and the wire becomes so hot that it glows and gives off light. It becomes so very, very hot, but it doesn't melt. This wire is made out of tungsten. And so here is a very high melting point for tungsten, while another metal like gallium has a low melting point. Okay, at this junction then, we want to go back and talk about the last type of crystal that we need to learn. And so this type of crystal is called a covalent networking crystal. Okay, covalent networking crystal. And for covalent networking crystal, the term becomes kind of problematic for us. We've used the term covalent when we talked about bonds. But now I'm talking about those forces that hold these particles together in the crystal structure. And so the term used here is covalent networking. It's more complicated, more complex. Because we've used the word covalent with bonds, that's why I changed covalent bonds to molecular on all tests. They'll refer to compounds like carbon dioxide and water as being molecular crystals. These crystals, like say of diamonds and graphite, they may say are covalent crystals. It might be called a networking crystal, or it could be called covalent networking. You need to be prepared for all of those possibilities. Let's look at some common examples of covalent networking crystals to see why these terms are used. To do this, we're going to look at probably the most common example of this type of crystal is carbon. And there are two allotropes of carbon, diamond and graphite, and you need to know everything about these. This will be in either chapter 10 or 11, depending on the textbook that you're using. So I'm going to start off by using Zumdahl's textbook right here. And in Zumdahl's textbook, let me see if I can zoom in a little bit. And you can see up in this corner the central carbon atom. Let's just focus on this atom right here. And this atom is bonded to 4 other carbon atoms. These 4 carbon atoms are sp3 hybridized. This means that it's tetrahedral in its directions. Bond angle maybe about 109. And what we would expect then is that these are bonds in many different directions. Remember that this is not a flat molecule. So in diamond, pure diamond, the electrons are said to be held very tightly in positions. For this reason, diamonds are extremely hard, and diamonds have extremely high melting points. This is the hardest material known, and diamonds melt at about 3,550 degrees Celsius. In contrast, if you look at graphite, nicely shown here, notice how there are carbon atoms within a plane. And let's focus on one carbon atom here. It is bonded to 3 other carbon atoms. So this is going to be an sp2 hybridization. Okay, each carbon atom there is bonded to 3 other carbons. So within the plane is held together by very strong covalent bonds. The planes don't like to break very much. They're hard to break. And so graphite is considered to be hard. But an unusual property of graphite, and what makes it different from diamond, is the fact that this black powder, the layers are held together by weak pi bonds. And the weaker pi bonds, the unhybridized 2p orbital used in the pi bonding, is considered to be delocalized and free to move. And so this makes graphite a very good conductor of electricity because you can have electrons moving along the line of the planes. And also because these bonds are weak, they can slip and slide past one another. This makes for graphite being, helps explain graphite being very good as a lubricant and being slippery. You find graphite in your pencils, and what happens is as you move your pencil across the page, layers of this graphite break off and deposit on your paper. The only other thing then that I will mention is going to be silicon dioxide. Let me get a picture here. This is from Zumdahl, and silicon is going to be the central atom here. And we say silicon dioxide. If we have SiO2, we have silica. Silica's formula is SiO2. But remember that silicon, like carbon in the same family, wants to make 4 bonds. So in silicates, you get the silicon bonded to 4 oxygen atoms. You should read about this very carefully because, because of the way the bonds are formed, silicon here satisfies the octet rule by forming single bonds with 4 oxygen atoms. And with the silicon at the center of this tetrahedral arrangement of oxygen atoms, which are shared with other silicon atoms. So it's a networking. If you were to think about the empirical formulas, I guess you would say, SiO4, the tetrahedra, is what you would have for the silicates. So the ratio of oxygen to silicon can vary from a 2-to-1 in silica to greater ratios of oxygen to the silicon in silicates and other compounds. Where would you want to be aware of this in common day occurrences is that, we'll move back to here, silica or silicates are found in substances like quartz. It's found in certain types of sand, and you may be aware of the fact that sand can be used to make glass. The other compound that I might mention is silicon carbide. You need to know these examples of covalent networking crystal. They are all, let me zoom out of this now for just a second. They are all held together by strong covalent bonds, and because of the tetrahedral arrangement, sp3 or sp2, this is going to be directed in many different directions, which gives it hardness. General properties then. Well, I guess you would say that these are going to be poor conductors. And then as far as melting points, we're going to say very high. Very high melting points. And very high hardness. Very high as far as their melting points and how hard they are. because of the bonding that occurs in many different directions. So, what would be at the lattice points? Wouldn't it just determine what crystal you're looking at? It could be in some cases like diamond or graphite, that at the lattice points what you have is carbon. But it could also be molecules. You can have SiO2 at the lattice points. So you have to look at the particular structure that you're studying. Please be very careful. Know examples specifically for covalent networking crystals. And I encourage you to read carefully in your textbook about their properties and how they form their crystal lattice.